Hey guys, today we are starting our notes over work, energy, and power. Today, specifically for this part of our video, we're going to be looking at work and then power and efficiency. So we're going to go ahead and just jump right into looking at work first. So a lot of this stuff you probably already know, so I'm going to go through it pretty quickly just because we've gone through a couple of different explorations on gizmos and done some labs on them, so it should be information that we're familiar with. It's just kind of solidifying what we know and what we understand. So work, we know, is the energy transfer that takes place when a force causes an object to move. So force is applied to an object, and then obviously the object then has to move some kind of distance. So our formula there, F times S. S we talk about just because D is used for a lot of different variables in physics. So here W is work, F would be your force, and then S is your displacement, so how far it is moved from its original position. Here, work, we can measure it in Newton meters. That's one way of measuring it. But that kind of standardizes into what we call joules, which joules will be really important when we get into talking about energy in the second half of this set of notes. So work can be measured in joules, or it can be measured in Newton meters, just because, again, newtons are the standard unit for my force, and then meters obviously are standard unit for distance. So straightforward example here, if we push a box across the floor at a constant force of 100 newtons, what is the work done by the force if it gets moved 5 meters? Pretty straightforward. 100 is my force, 5 is my distance, so 500 joules would be that, that work done to push the box. If the floor is smooth, where does this energy go? Well, the box accelerates and gains kinetic energy, which we'll talk about in a little bit. If the floor is rough, some of that energy is going to be lost to that friction in the form of a sound or some kind of heat that's created with the friction between the floor and the box. Now, it does change, our formula does change slightly if we have a force applied at an angle. So if we're not just pushing straight forward, if we're either pushing upwards from behind the box, or we have something attached and we're kind of towing it. If we're not towing it straight horizontal from where it's attached at, if we have an angle there, we have to adjust the formula slightly, because the box can move in a different direction than where the force was applied at. Because anytime we're talking about work done, that distance has to be in the direction of where your force is going. So like when we calculated work done for the stair climbing lab, we focused on just one aspect of it, just that vertical work done. So we looked at the power of getting ourselves from the bottom level to the top level of the stairs. And so that angle, we kind of just simplified it down into just a single thing. But when we have work done at an angle, it's going to change how we calculate it. So we'll break it down again into those components, just like we did back when we did two-dimensional motion with our projectile motion. It can be broken down into horizontal and vertical components, where we have the force acting at an angle, the horizontal and the vertical aspects of it, the two components of that force applied. Depends on the angle that the force happens at, and it also depends on which way we're measuring the work done. In the case of pulling the box along, we're doing horizontal work because we're just dragging the box across. There might be cases like where what we were working on with the stair climbing lab, where we're focusing on the vertical force, the vertical work done. That might be different, but in most cases, when you're pulling the box along, you're going to be dragging it. So there's actually no vertical work done because there's no distance moving up and down. It's all horizontal. So we get to simplify that formula down so that work done is equal to the force in the direction of the movement, distance is moved. So this ends up being our new formula. When we have force applied at an angle, and again, we're assuming here that it's a horizontal movement, this is our new formula. Basically, again, still force times the distance that it travels, we just have to multiply in times the cosine of whatever angle the force was applied at. So we'll take a look at an example of what that looks like. Here we have a toy car that's pulled along a piece of string. It's at 30 degrees to the horizontal. The work done, we're trying to calculate the work done by pulling the car if the tension on the string, so the force applied, is 10 newtons and is pulled along for 5 meters. So we've got all three of the things that we would need for this calculation. We have our force of 10 newtons. We have our distance of 5 meters is how far we're pulling the car. and we have what angle that rope is being that force is being applied to. So again, just plugging in for our formula: force of 5 newtons, distance of 10 newtons, distance of 5 meters, and then our angle is 30 degrees, so cosine of 30. You multiply all three of those together, and we get 43.3 joules. So just some true or false here, just a quick summary. Work is done whenever a force moves an object. That is true, because again, there's a distance that our object moves, and it is because a force was applied, there was work done. Number 2 here, work is done whenever a force is applied to an object. That's not true. It's only if that object moves, right? I could push against a wall all day long and apply a force to it, but if there's no movement of that wall, I don't do any work. It feels like I've done work, but I haven't actually done any work in the scientific sense. The amount of work done depends on the distance moved. Definitely true. Number 4, the amount of work done depends on the size of the force applied. Again, that is also true. How much force is applied does change how much work was done. A greater force means a greater amount of work. A smaller force means a smaller amount of work, assuming distances stay the same. And then the last one, a little tricky, and I'm not as concerned with number 5 here as the other 4. Work done can be calculated from the gradient, meaning the slope of a force distance graph. That is true. If we looked at, if our vertical component was our force, or horizontal component was our distance, we could figure out what the slope is and then see, all right, well, here's the force that was applied in this particular point, and then this was the distance that was traveled because of that. So you can work backwards to figure that out from your slope. All right, so getting into part 2 of our notes here on power and efficiency. Power, very, very similar to work, except now instead of just looking at how much total work is done, we're looking at the rate at which work is done. So still taking that same idea of force and distance, but now looking at, again, the rate at which it's done. So obviously we're taking that work done divided by time, so how long it takes to do that work. So that's the equation. P is work over time. Measurement here, our standard unit is watts, W-A-T-T-S, as in like J.J. Watt, T.J. or Derek Watt. Work done or energy transferred, again, that's measured in joules, is our standard unit. That could be, again, Newton meters, since that is coming from our force and our distance. Our force and distance. And then dividing that by time, that standard unit, again, is in seconds. So those are all of our standard units for all of those things. Watts would be the measurement of how much power we have. So like when we talk about the wattage of a light bulb, it's how much power it uses, how much work it is possibly done, divided by how long it takes to do that work. All right, jumping into some examples here. A crane lifts a load of 15,000 kilograms, a height of 25 meters at a steady rate. In the time of 2 minutes, what is the power of the crane? So again, here, very straightforward. We have all the information that we need right away. We don't have to interpret anything since we have our 1,500 kilograms and our 25 meters. That's our this 1,500 kilograms. This is our mass. So what we have to do is convert that into our work done. You'd have to take this times the acceleration that has to work against due to gravity. So very similar to what you guys had to do for the power stair climbing lab, where you took your mass, I think most of us measured it in pounds, and then I gave you the conversion to get into newtons, so into our weight instead of our mass. Kind of the same idea here, 1,500 kilograms times the acceleration due to gravity times the height would be that work done. So this is using a slightly different formula. I decided to go a little bit out of order of how I usually do the notes. So this is something we'll talk about in part 2, the second video, part 3 of our notes, with looking at potential energy. But same idea here with our work done being our mass times gravity. That's our force due to the weight that it's lifting, the load that it's lifting, times the height that it's going at. So different looking formula, but the same general idea, where work is your force times your distance displaced. So here our force would have to be 1,500 kilograms times the 9.81 is what I used here. 9.8 is fine. Times the 25 gives me 367,875 joules. So if that is the work done, that's how many joules of work were done to lift that big load up to 25 meters. If we know it took 2 minutes to do that, what we have to convert into is make sure that, again, standard unit is seconds. So 2 minutes would be 120 seconds. So we'll just divide that to get 3,066 watts. 3,066 watts. All right. Next section here, the power outputted by a powered object, such as an engine or muscles, is sometimes called motive power. If the object is powered at a constant speed, at a constant height, then we can just talk about its power being the force that it's exerting times the speed it's traveling at. So, again, this is something that is self-powered. Motive power is in, like, it is powering itself. Again, an engine is an example of this. Muscles, they power themselves. Nothing is being, like, no object or thing is acting on what's moving. It's self-powered. So again, here, the force that it exerts, and then the velocity or the speed that it travels at. So here again, at a constant speed and height, the force produced by the powered object is equal but opposite to all the resistive forces acting on the object, such as friction and air resistance. Again, that makes sense. If we're holding those two things constant, if we're keeping that speed constant, and we're not changing the height, we're not displacing it all, again, then the force would have to be equal and opposite, right? If we're in a balanced system with no change in velocity, we're not accelerating at all, then those forces have to be balanced, because we know if we have an unbalanced force, it's going to cause an acceleration. So here, if we're at a constant speed without changing the height, meaning there's no acceleration happening, then the force that it's exerting has to be equal and opposite to whatever forces are acting on it, whether that's gravity, friction, air resistance, whatever it is. Okay. Example number 2. What is the resistive force on a cyclist who has leg muscles of power 200 watts each and reaches a top speed of 10 meters per second on a level road? And don't get thrown off by this. This is just a weird way. I just have this slideshow from many years ago when I first taught physics, and now it's not an editable thing. So this is just how they wrote meters per second. So seconds to the negative first power instead of meters over seconds, meters per second. This is just, again, the speed in meters per second. And we have the power of each leg. So with this, again, going back to knowing that this is our formula for power. If power is equal to force times speed, here we know the speed, we know the power. We can work backwards to figure out what that force would be. Because here, if we're using this formula, again, rearrange. You can plug it in, or you can rearrange it first. It's up to you guys on what your personal preference is. I usually just plug stuff in and then solve for the variable I need. I probably wouldn't even do this. I would go ahead and just plug right away 200 watts in here for my power. I know my velocity is 10 meters per second, and then I would just divide by 10 on both sides. But here, just for funsies, we can divide by V on both sides to get F by itself. So then our power divided by our velocity would give us what that force is. So 200 times 10, 200 times 2 again here, because this power is of each leg, and from the picture here we can see that the cyclist has both legs. So 200 times 2, and then dividing by that 10 meters per second for our velocity gives us a total of 40 newtons. So that's how much force the cyclist is actually producing to accelerate forward. Therefore, the resistive force acting on it has to be equal and opposite to that. All right. Efficiency. So very similar to power, efficiency is still a rate. But here, if we're talking about the efficiency, it's kind of like grading how well the power is exerted. So it's a ratio, so it's just a percentage or a fraction of useful work done by the device to the total work done by the device. So the ratio of, again, output energy to the total energy input. So in a perfect system, the exact amount of energy that we're putting into it is the exact amount that we would get out of it. So useful work done divided by total work done, or again, useful energy output versus useful energy input. It's, again, usually expressed as a percentage. It's always less than 100% because there's no perfect system where no energy is lost, just because we have resistive forces and all that stuff. For example, what's the efficiency of a 60-watt filament lamp that gives out only 1 watt of light? So here again, looking at how much we're getting out of the object, the system, the scenario, whatever it is, versus how much it takes in. So in this case, a light bulb that takes 60 watts of power in order to heat the filament up inside the lamp or inside the light bulb, but it only puts out 1 watt of useful light. Well, again, useful energy or useful power divided by input or total work done, total power, would be 1 over 60, so 0.017, which if we look at again as percentages, move the decimal place 2 to the right, 1.7% effective. Not very effective. This next idea here, Sankey diagrams, it's something that we may or may not cover on the test. I have to take a look and see. I don't think it's something that I usually include. It's something that as you get more into like engineering side of things, or if you get into the more technical side of physics, it's a way of us kind of visualizing the energy input versus the energy output, and like where the system loses energy, where the system, gives off different forms of energy. And it's kind of like a flow chart where it all starts at whatever the input is. Sometimes here, so you can see that this input is electrical energy. We start up with 100 watts of power that is put into this system. 5 watts end up as light energy, so it emits 5 watts of power. But you can see, obviously, this other 95 watts doesn't go nowhere in that system. If 5 watts are put out as light energy, we can see here it kind of diverts off and says, all right, well, the other 95 watts are given off as heat, because it has to go somewhere. It can't just disappear. That's something we'll talk about in part 3 of the notes for this section, video number 2, the law of conservation of energy, where energy is not created nor destroyed, just converted between different forms. So if we still have 95 more watts of energy, we have to make sure that we account for that somewhere. We have to figure out where that went. All right. So here again, we can do some calculations in this question, just this one in particular that's up here. A pump lifts water in a house if it can lift 1.5 kilograms each second through a height of 20 meters. What is the power of the pump? And here we're assuming that there's no energy lost. So what we'd have to do first, and you can already see some of the steps that were done here, you would have to figure out the work done by that pump. So here, if you can lift 1.5 kilograms each second for a height of 20 meters, you would have to start with 1.5 times 9.8, because that would be the force required to lift 1.5 kilograms. Right, that our force is always our mass times our acceleration from way back when. So 1.5 times 9.8 gives us that 4.7 that you can see here at the top of this box. And that times your distance would be your work done. So again, your force times your distance is your work. So 294 joules is how much work is done by that pump. So 1.5 kilograms, height of 20 meters, that's 294 joules. To calculate the power, you're looking at how often or how much time it takes to do that. Here in this case, every second it does that amount of work. So dividing it by 1 is super easy. It's just the same thing. If we do it per second, 294 watts is the power rating of that pump. And that's it for work and power. So this is where we're going to cut off today. Tomorrow, I'll be posting the second video just for part 3, which is all about kinetic and potential energy. That one should be a little bit of a shorter video than what was today. But as always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. And have a fantastic day.